Good morning, everyone. Now, today we will start with the new module, that is module number 2, that is gas power cycles. The syllabus for this is gas turbine, Brayton cycle, description and analysis, regenerative gas turbine cycle, intercooling, reheating in gas turbine cycles, introduction to jet propulsions. Gas turbines and jet propulsions. It comes in module 2, it's not module 3. So mainly the syllabus covered here will be classification of gas turbines, analysis of open gas turbine cycle, advantages, disadvantages, then methods to improve thermal efficiency, jet propulsion and rocket propulsions. So the gas turbine can be classified into two types. One is constant pressure combustion gas turbine. In that we have a open cycle constant pressure gas turbine and a closed cycle constant pressure gas turbine. So next is constant volume combustion gas turbine. So in an open cycle gas turbine, the gas or air is not will not be reused again and again. So the gas turbines are basically prime movers. They convert the heat energy into mechanical energy. They are widely used in aircraft and industrial installations. So first of all, the air enters the compressor. The air is compressed to a high pressure, then it is passed into a combustion chamber where fuel, liquid, solid fuel is also being the liquid fuel may be sprayed into the combustion chamber. The air and fuel mixture undergoes combustion at a high temperature. So at a very high pressure, then it is made to pass into the turbine. The turbine, as it passes over the gas turbine, it undergoes expansion and work is produced. This is the work output. This is the work input by the compressor. Normally, the turbine runs the compressor. The turbine and compressors are coupled together. So the turbine runs the compressor. Heat in the combustion chamber is added at a constant pressure. In a compressor, the air is compressed at a constant entropy or isentropic compression takes place in the compressor and isentropic expansion takes place in the turbine. You can see here air from the atmosphere is getting compressed 1 to 2. Fresh air gets compressed at a constant entropy, then or we can say adiabatically. That is, adiabatic means there is no addition of heat. That is, the heat remains constant during the process 1 to 2. There is neither heat addition or not heat rejection. Then from 2 to 3 it undergoes combustion at a constant pressure in the combustion chamber. Then these hot products are made to pass through the turbine and where it undergoes expansion at a constant pressure and work is produced, that is W output. W net is nothing but W work of the turbine minus work of the compressor. As I said earlier, the turbine is coupled to the compressor. So the work is taken from the compressor and used to compress the air. Next is pressure versus volume diagram for a Brayton cycle. So the pressure versus volume diagram. So you have a 1 to 2 compression of air. You have a 1 to 2 compression of air at constant entropy. Constant entropy means adiabatic. There is no heat addition or rejection from this process and the entropy remains constant. So pressure versus volume diagram, 1 to 2 entropy remains constant. In the same way we can see in a temperature versus entropy diagram, 1 to 2 the entropy remains constant. 1 to 2 in a PV diagram, 1 to 2 in a TS diagram. Temperature versus entropy, pressure versus volume. Then you have a 2 to 3, it is a heat addition. So what happens in 2 to 3 is it is a heat addition. It takes place in a combustion chamber where air and fuel mixture undergoes compression at a constant pressure. You can see 2 to 3 is a constant pressure process. 2 to 3 constant pressure process. You try to look at both the PV and TS diagram. So for constant pressure, you look here, so we can see the pressure is constant. Next, 3 to 4 is an expansion process where work is done. So here it is a constant entropy process. You see the straight line, 3 to 4 is a constant entropy. You can see 3 to 4 the pressure changes. Whenever pressure changes, obviously there is a either compression or a expansion. So here 3 to 4 is along the positive axis. That's why it is a work done. Here 1 to 2 is along a opposite, that is negatively we are moving, the pressure is getting reduced 1 to 2, so it is a compression. The next is 4 to 1 is heat rejection. So if it is an open cycle, it is the products of combustion are left out into the atmosphere, that is heat rejection. If it is a closed cycle, it is the gases are the heat is rejected from the gases by using some cooling mechanism. So we can say two adiabatics. Two adiabatics are two isentropes. So two adiabatics. 1 to 2, 3 to 4. Then two isobars. 2 isobars, 2 to 3 and 1 to 3. So in this slide also we can see two reversible adiabatics. That is adiabatics 1 to 2 and 3 to 4. Then you have a two reversible heat additions at a constant pressure 2 to 3 and 4 to 1. So we will try to analyze this whole cycle. So we are neglecting the kinetic and potential energies, and also we are assuming it as a steady process. It means to say it does not change with time. It is constant, that is it is steady flow. The process, heat, work, all the parameters don't change with time. So we can say 1 to 2. So 1 to 2 is a reversible adiabatic process. Here 1 to 2 work is being done. So you can see 1 to 2 reversible adiabatic process, work is being done. Whenever it is adiabatic, we know that there is no heat addition or rejection. Q 1 to 2 is 0, but the work is being done. Work done can be given as specific heat of gases into delta T, that is change in temperature. The gases enter at a particular temperature and leave at a particular temperature. So if it is work input, that is T2 minus T1. If it is work of compression, that is again change in the specific heat into change in temperature. So 2 to 3. 2 to 3 is a heat addition process, because 2 to 3 is process takes place at a constant pressure. So whenever anything takes place at a constant pressure, the work done will be 0, because there is no change in pressure, no work done. 2 to 3, we can again say heat addition process is Cp into T3 minus T2, that is positive heat addition. Then you have a heat addition can be given by Q1 is equal to Q2 to 3, that is the T3 minus T2. The gases enter at a lower temperature, leave at a higher temperature. Then 3 to 4 is a work done. So because here 3 to 4 is an adiabatic process or isentropic process. Whenever there is an adiabatic, no heat addition, no rejection. So Q3 to 4 is equal to 0. W3 to 4 is given by specific heat of gases into change in temperature. So the gases enter at a higher temperature but leave at a lower temperature. So T3 minus T4. So if it was compression, it would be reverse, because the gases enter at a lower temperature, leave at a higher temperature, that is T1, T2 minus T1. Here it is T3 minus T4, entering at a higher temperature, leaving at a lower temperature. So 4 to 1. 4 to 1 is again a constant pressure process, because it is a closed cycle gas turbine. The air gets circulated throughout the cycle and heat is being added externally, heat is being rejected externally. There is no, in a closed cycle turbine, there is no mass transfer between the system and the surrounding. only there is a energy transfer. So there are both types of gas turbines, open and closed cycle. This is closed cycle. Only energy transfer, that is heat transfer, work transfer takes place, no mass transfer takes place from this system and the surrounding. Then 4 to 1 is also a constant pressure process. Whenever there is a constant pressure process, work done is zero, obviously. So no change in pressure, no change in work. Means you cannot have a work done without change in pressure. But there is a heat rejection to the surrounding, that is T1 minus T4. So T4 is higher temperature, T1 is the lower temperature. So T1 minus T4. So it can also be written as minus Cp T4 minus T1, where negative indicates the change in heat rejected. So heat rejected is equal to Q2 is equal to Q41 Cp T4 minus T1. We know that efficiency is nothing but output by input, that is work divided by heat input. So how can we write this? So output is work. Work is nothing but Q1 minus Q2. Input is Q1. So it can be written as 1 minus Q2 by Q1. That is, we know Q2 is what? Cp T4 minus T1. We know from earlier. Q2 is equal to from earlier diagrams, Q2 is T4 minus T1. Q1 is what? Cp into T3 minus T2. So we substitute Q2 and Q1, Cp into T4 minus T1, T3 minus T2. So because specific heat is same, Cp gets cancelled. What remains is T4 minus T1 and T3 minus T2. So we already know that for an isentropic process, what happens 1 to 2 is, for an isentropic process 1 to 2, the change in temperature and change in pressure relation can be written as T2 by T1 is equal to P2 by P1 gamma minus 1. And also for an isentropic process 3 to 4, the formula can be written as T3 minus T4 and P3 minus P4. So now we know that P3 is equal to P2, P4 is equal to P1. Look here, P3 is equal to P2, P4 is equal to P1. So obviously P2 by P1 is equal to P3 by P4. So we can just both of them we can just equate them. That is T2 by T1 is equal to T3 by T4. So T3 by T2 by T1 is equal to T3 by T4. Rearranging it, T4 and cross multiplying that, T4 by T1, T3 by T2. Subtract minus 1 on both sides. Minus 1 on both sides. What you do is subtract minus 1 on both sides here. So it becomes T4 minus T1 minus 1, T3 minus T2, T3 by T2 minus 1. So then take T4 by T1 minus 1, that is T4 minus T1 by T1, T3 minus T2 by T2. So next is just cross multiply this, T4 minus T1, here it goes, T3 minus T2 is equal to T1 by T2. So next is, after cross multiplying T4 minus T1 and T3 minus T2, and this goes up, T1 minus T1 by T2. So we know that T1 by T2 in terms of volume is V2 by V1 for an isentropic process, and P1 by P2 is equal to gamma minus 1 by gamma for an isentropic process. So we know that compression ratio is equal to volume V1 by V2, that is specific swept volume plus, that is volume, initial volume V1 divided by volume, final volume V2. we know our equation that gamma is equal to 1 minus T4 minus T1 divided by T3 minus T2. So we will substitute instead of this whole term T4 minus T1 and T3 minus T2 by, so instead of writing T4 minus T1 divided by T3 minus T2, we write V2 by P1 gamma minus 1. So we can see instead of writing T4 minus T1 divided by T3 minus T2, what I will write is, we have got a expression here, T3 minus T1 divided by T3 minus T2 is equal to T1 by T2. So T1 by T2 is equal to V2 by V1 gamma minus 1. Instead of that, I will substitute the value of V2 by V1 gamma minus 1 in place of this. In place of this, I am substituting V2 by V1 gamma minus 1. So what happens is, you can see I have substituted there. So return efficiency becomes V2 by V1 gamma minus 1. So if we take reciprocal of this, it becomes V1 by V2. We already know that what is compression ratio? It is V1 by V2. If we reverse this V1 by V2, what it becomes? What it becomes is V2 by V1, that is 1 by V1 by V2 is equal to compression ratio, that is 1 minus 1 by RC gamma minus 1. Or instead of that, we can write it as, instead of writing this V1 by V2, sorry V2 by V1, we can also write P1 by P2 also. So the other form is P1 by P2 gamma minus 1 by gamma. So we know that RP, that is pressure ratio, is equal to P2 by P1. So taking the reciprocal of this P2 by P1, that is RP gamma minus 1 by gamma. It can be seen that for the same compression ratio, efficiency of Brayton cycle is equal to efficiency of Otto cycle. Closed cycle turbine plant is used in gas cooled nuclear reactors where the source is a high temperature gas cooled reactor supplying heat from a nuclear fission directly to the working fluid. So there is no you don't use directly the heat, but you exchange the heat from a heat source to the working fluid. That is how it is a closed cycle. You need not you are going to use the working cycle again and again. Thank you.